challenging aspects of working with Laplace transforms is that Laplace transforms are complex functions of complex variables, which makes them quite difficult to visualize. Now, if we think about visualizing or plotting a normal function, in other words, something like the sine of t, it's very easy for us to see how to do that because we can use one axis for the time and we can use another perpendicular axis for the function value. And in this way, every possible combination of time and function value can be mapped out onto a two-dimensional plane. But notice that in order to plot a function which is a scalar function of a scalar input, in other words, we had a scalar time and a scalar function of time, we needed an axis for time and an axis for the function of time, which led us to have a two-dimensional plot. Now, so I'm going to use dimensions and variables a couple of times in this video. So just keep everything straight. When I'm talking about a one-dimensional function, what I mean is that this function returns a value which is one-dimensional. And in this case, it's also a function of a one-dimensional variable. You'll also hear me say scalar to mean one-dimensional. So a scalar function of a scalar variable can be plotted completely on a two-dimensional frame, one dimension for the input and one dimension for the output. It gets a little bit more challenging when we have more than one dimension in the input or output, but we can still kind of deal with that. So here we have a vector, a scalar function of two input variables. So we have an x and a y, and it's possible for us to plot that on a three-dimensional chart. Now, please note, this is a pseudo three-dimensional chart. In other words, it looks three-dimensional, but in fact it is being projected onto the two-dimensional screen. If you're watching this on YouTube, you'll see, if you're watching this on YouTube, you will have to agree that your screen is two-dimensional, even though this seems three-dimensional. So we can see the same idea, instead of using a height, but rather to use colors to represent the third axis. So here we've got the x and the y, and we're using a color. In this case, the yellow values are the high values and the black values or the purple values are the small values. So this is about as far as we can go with the dimensions that we live in, because we only have three dimensions. And so it's possible we could build a model like this, a little eggshell or egg holder kind of function, where we could actually build something like this in three dimensions. But we're faced with a bit of a challenge when we have a complex function of complex variables. Because so if I have something like g of s, then actually I have two input variables, the real and imaginary part of s, and two output variables, which are the real and imaginary parts of g of s. Now I'm going to switch to GeoGebra quickly to just give you an idea of what I'm talking about by a two-dimensional mapping like this. The nice thing about GeoGebra is that it actually has quite rich support for complex numbers. So I can create a complex number, I can call it S, and at this point I can move S around the plane, and GeoGebra will show me the real and imaginary values. So you can see this is just a normal point on a plane. Now I can also define G of S, and I can define that to be, and what I want you to see is that there's a mapping. I've got this function that is defining the mapping. I have S, which is this point that I'm moving around, and I have this point Z, which is now G of S. As I move S around g of s moves. And something that's already interesting to note is that as s approaches the point -1, z, which is now g of s, moves further away from the origin. And so we'll see that that's going to be quite important later when we start plotting more interesting functions. But this idea that a point in S maps through the transfer function or through this function of S to another point, and both of them are complex points, is an important point to understand. And so at the value of the pole, we can see that Z becomes undefined, and we can see that g of s has a pole at -1, which is over there. Now, wouldn't it be nice if we could actually see what those poles look like? And yes, there are ways of doing this. We can do this using the MP Math library, and we can see that we can plot a transfer function, and this is a second order undamped transfer function. We can plot this using a system where we encode the color is encoding the angle of g of s, and let me just make sure that everybody understands this. So what I mean by that is that that g of s can be thought of as a vector. So we can see for lots of different values of s, as s approaches that pole, I can see that the vector is making a particular angle with the positive real axis, and the vector is getting taller or longer and longer as I get closer to that pole value. Now we can see something similar to the function that we have in the notebook. If we plot those poles, we now see that we can see that the poles are around here. They're around 1 on the imaginary axis, so 1 imaginary and -1 imaginary, and around a half-ish on the real axis, and so that's basically where those values are. This domain coloring allows us to see what the angle is, and so the color is defining the angle, and the brightness is defining the magnitude. In this visualization, I am highlighting the domain coloring. So I've got the same domain coloring. I've got here the colors are showing the angle that g of s makes with the real axis, and so my mouse is moving s, and the other point that you see connected to the triangle is g of s. I've plotted the poles, and you can see when I move onto the poles, the magnitude of g of s becomes very large or infinite. So those are the brightest points, and you can see that as I move along a area of similar color, so let's stay on this magenta line, the angle that g of s makes with that axis is always the same. Now, another very important point to see on this visualization is that I have plotted the real and imaginary part of e to the st. And so the red line and the blue line over here are the real and imaginary parts respectively. And an important thing to see is that at the point defined by the poles, I am seeing very similar behavior to what I expect the response or the impulse response of the system with this transfer function to have. So notice that when the S is on the pole, that the shape of the imaginary part very closely resembles the actual impulse response. Now we can actually get that to match up 100% by just playing around a little bit with the gain, and we can see at this point the imaginary response of e to the st matches exactly what the impulse response looks like. Now this is a general rule. When s becomes equal to the pole, e to the st resembles the impulse response, or at least resembles a part of the impulse response. The true impulse response will be a linear combination of the responses at the poles. In this case, we see that we have to multiply both of these by minus I in order to obtain the response that we're looking for. Now that will cancel out the real part, but we'll retain this imaginary part.